Good afternoon. Now I am going to discuss you about the real analysis second section. So in this chapter we are going to discuss about the properties of monotonic functions, functions of bounded variations, total variation, additive property of total variation on a comma x as a function of x, function for bounded variation expressed as the difference of increasing functions, continuous functions of bounded variations. So first case, the first property of monotonic function is, let f be an increasing function defined on the closed interval a comma b, and let x naught, x1, etc., xn be n plus 1 point such that a from a equal to x naught less than x1, etc., less than xn equal to b. Then we have the inequality summation of f of xk plus minus f of xk minus less than or equal to f of b minus f of a. So this xk plus, we have discussed already that the right hand derivative of f at xk, and f of xk minus denotes the left hand derivative of f at xk. So to prove this, first let us assume that yk is an interior point which belongs to the kth subinterval, say xk comma xk plus 1. For 1 less than or equal to k less than or equal to n minus 1, we can have f of xk plus less than or equal to f of yk, and f of yk minus 1 less than or equal to f of xk minus. So that we can write f of xk plus minus f of xk minus is less than or equal to f of yk minus f of yk minus 1. So if we add these inequalities, the sum on the left hand side tends to f of y n minus 1 minus f of y naught. Since f of y n minus 1 minus f of y naught is nothing but f of b minus f of a. So hence we have the inequality that the sum of the difference between the right hand derivative and the left hand derivative is less than or equal to f of b minus f of a. So here the difference between the right hand derivative and the left hand derivative is of course the jump of f at xk, that is f of xk plus minus f of xk minus denotes the jump of the function f at the point xk. The foregoing theorem tells us that for every finite collection of points xk in the open interval a comma b, the sum of the jumps at those points is always bounded by f of b minus f of a. So now we are going to prove the next one. If f is monotonic on the closed interval a comma b, then the set of discontinuities of f is countable. So since f is a monotonic function, so it may be a non-increasing or non-decreasing or both. So let us assume that f is an increasing function, and let Sm be the set of points in the open interval of a comma b at which the jump of f cannot exceed 1 by m, where m is greater than 0. If x1 less than x2, etc., less than x n minus 1 or in Sm, then the theorem tells that n minus 1 by m less than or equal to f of b minus f of a. By using the previous theorem, we can say that the difference between the right hand derivative and the left hand derivative always bounded by f of b minus f of a. So based on this, here we can say that this is less than or equal to f of b minus f of a. This means the sum Sm must be a finite set, but the set of discontinuities of f in the open interval a comma b is a subset of the union, and hence f is a countable one. Next one, functions of bounded variations. If closed interval a comma b is a compact interval, a set of points p from x naught to xn satisfying the inequalities a equal to x naught less than x1, etc., less than xn equal to b is called a partition of the closed interval a comma b. The interval xk minus 1 comma xk is called the kth subinterval of p, and we write this as delta xk equal to xk minus xk minus 1, so that the summation of delta xk is nothing but b minus a. So the collection of all possible partitions of the closed interval a comma b, we used to denote it by capital P of a comma b. So p denotes, that is P of a comma b denotes the set of all partition, that is possible partitions in the given interval. Next definition states that f be defined on the closed interval a comma b if p varies from x0 to xn, which is a partition of closed interval a comma b, and we can write delta fk as f of xk minus f of xk minus 1 where k varies from 1 to n. If there exists a positive number m such that summation of modulus of delta fk is less than or equal to m for all the possible partitions of closed interval a comma b, then we can say that f is said to be of bounded variation on the given closed interval a comma b. So, example for the above. And third theorem states that if f is monotonic on a comma b, then f is of bounded variation on a comma b. So, since f is monotonic on a comma b, so let us suppose that f is an increasing function on a comma b, then we consider the partition. For every partition of a comma b, we have delta fk greater than or equal to 0, and hence we can write this as summation of modulus of delta fk is nothing but delta fk, and this is equal to summation of modulus of f of xk minus f of xk minus 1, and this is nothing but f of b minus f of a. So, thus f is a function of bounded variation, and the converse of the theorem need not be not true. Here it is an example for the function which is of bounded variation, but it is not monotonic. So, next theorem states that if f is continuous on the closed interval a comma b, and if f dash exists on closed interval a comma b and is bounded in the interior, say f dash of x less than or equal to a for all x in the open interval a comma b, then f is of bounded variation on the closed interval a comma b. So, to prove this, we consider a partition P of a comma b where P from x0 to xn such that a equal to x0 strictly less than x1 less than x2 etc. less than xn equal to b. Now, by applying the mean value theorem for the function in the given interval xk minus 1 comma xk, we can write delta fk equal to f of xk minus f of xk minus 1. That is nothing but f dash of tk into xk minus xk minus 1. Here tk is an interior point in this subinterval. So, if we take summation, sum of k varies from 1 to n modulus of delta fk equal to summation of modulus of f dash of tk into modulus of xk minus xk minus 1. So, since by the given data f dash of x less than or equal to a, so applying this, here we get the inequality less than or equal to a into summation of delta into xk. Therefore, delta into b minus a, that is delta xk is nothing but xk minus xk minus 1, and that is equal to b minus a. So, this entire term is equal to m for all partitions of a comma b. So, hence f is a function of bounded variation on the closed interval a comma b. And since again it is an example for the above bounded variation. And fifth theorem states that if f is of bounded variation on closed interval a comma b, say summation of modulus of delta fk less than or equal to m for all the partitions of closed interval a comma b, then f is of bounded on a comma b. In fact, modulus of f of x less than or equal to modulus of f of a plus m for all x in the closed interval a comma b. Or we can say that a function f is of bounded variation over the closed interval a comma b is also bounded. So, to prove this, let us consider x belongs to the closed interval of a comma b and consider the partition P which contains a, x and b of the closed interval a comma b. For this partition P, we consider modulus of delta fk equal to f of x minus f of a, that is the partition we use it to split with the help of x. So, we can write modulus of f of x minus f of a plus f of b minus f of x which is less than or equal to m. In particular, modulus of f of x minus f of a less than or equal to m, and so that we can write modulus of f of x is less than or equal to f of a plus m for all x belongs to the closed interval of a comma b. So, whenever a function is of bounded variation is bounded. Then total variation, Let f be of bounded variation on the closed interval a comma b, and let summation of p denote the sum of modulus of delta f k corresponding to the partition p from x naught, x1, etc. xn of the closed interval a comma b. The total variation Vf of a comma b is defined as supremum of summation of p such that for every p belongs to capital P of a comma b, which is called the total variation of f on the closed interval a comma b. So, here the small p denotes the possible partitions of the given interval and which belongs to the set of all partitions say P of closed interval a comma b. So, therefore, the total variation Vf of a comma b is equal to supreme of summation of all the partitions of P. Assume that f and g are each of bounded variation on closed interval a comma b, then their sum, difference and product also we have, that is V f plus or minus g less than or equal to V f plus or minus V g. Here V f denotes the total variation of f, similarly for g also, and same like that V f g less than or equal to A V f plus B V g, where A is supreme of modulus of g of x for every x in the closed interval a comma b, and B is the supreme of modulus of f of x for every x belongs to the closed interval a comma b. So, to prove this, let us define h of x as f of x into g of x for every partition p of the closed interval a comma b. Now, we consider the modulus of delta h k, which is defined as modulus of f of x k into g of x k minus f of x k minus 1 into g of x k minus 1. That is, for our convenience, here we are adding and subtracting with f of x k minus 1 into g of x. So, in next step we are having modulus of f of x k g of x k minus f of x k minus 1 g of x plus f of x k minus 1 g of x plus f of x k minus 1 into g of x k minus 1. Now, we are splitting this into 2, that is modulus of f of x k minus f of x k minus 1 into modulus of g of x k, and similarly the second one. So, from this we have got A into modulus of delta f k plus B into modulus of delta j k. Therefore, summation of modulus of delta h k is less than or equal to modulus of delta f k, that is A into modulus of delta f k plus B into modulus of delta g k. This implies that h is of bounded variation and hence Vh less than or equal to A Vf plus B Vg. So, similarly we can prove the other also. That is, here we have considered, we have defined that h of x as f of x plus g of x, and we consider the partitions phi of a comma b, and modulus of delta h k can be expressed as modulus of f of x k plus g of x k plus modulus of g of x k. So, this is less than or equal to modulus of f of x k minus f of x k minus 1 plus modulus of g of x k minus g of x k minus 1, and that is equal to modulus of delta f k plus modulus of delta j k. Thus, which shows that Vh is less than or equal to Vf plus Vg, and similarly we can prove that Vh is less than or equal to Vf minus Vg, that is V of f minus g less than or equal to Vf minus Vg. So, next definition states that a function f is from the closed interval a comma b to R is said to be bounded above from 0 if there exists a positive number lambda such that modulus of f of x greater than or equal to 1 for every x belongs to closed interval a comma b. Equivalently, in x belongs to a comma b, modulus of f of x is greater than or equal to 1. Next theorem, let f is from closed interval a comma b to R be a bounded variation on a comma b and also bounded above from 0, then g equal to 1 by f is also of bounded variation on a comma b, and Vg is less than 1 by m square into Vf, where modulus of f of x greater than or equal to m, which is greater than 0. So, to show that, we consider the partition P of the closed interval a comma b, and we can write this as P equal to summation of modulus of g of xk minus g of xk minus 1. Since g equal to 1 by f, so we can write the above as 1 by, that is summation of 1 by f of xk minus 1 by f of xk minus 1. That is, if we cross multiply this and we get finally 1 by m square into summation of p, where p belongs to p of closed interval a comma b, and that is nothing but 1 by m square into vf. Thus, Vg less than or equal to 1 by m square of the total variation of f. And the additive property of total variations. Let f be of bounded variation on the closed interval a comma b, and assume that c belongs to a comma b, then f is of bounded variation on the subinterval say a comma c and on c comma b. Now we have the total variation of a comma b is nothing but vf of a comma c plus vf of c comma b. So first we are going to prove that f is of bounded variation on a comma c and on c comma b. So for that, let us consider two partitions, say p1 and p2, and p1 is a partition of the closed interval a comma c and p2 be a partition of c comma b. Then p is a partition which is equal to p1 union p2 of the closed interval a comma b. So for, let us consider p1 equal to from a to c, and the points are a0, a1, etc., am equal to c, and p2 from c to b. Then p1 union p2 is from a to b. The summation of p denotes the sum of modulus of delta fk corresponding to the partition p, and we can write this as summation of p1 plus summation of p2, which is equal to summation of p, that is less than or equal to the total variation of a comma b. Since summation of p1 and summation of p2 are both non-negative, so summation of p1 less than or equal to vf of a comma b, and summation of p2 less than or equal to vf of a comma b. Then f is of bounded variation on the both subinterval a comma c and c comma b. Further we have the total variation, say vf of a comma c minus c comma b can be expressed as supreme of summation of p1 plus supreme of summation of p2, and that is nothing but summation of p1 plus p2, which is equal to the total variation of a comma b. Now to prove the reverse inequality, vf of a comma b is less than or equal to vf of a comma c plus vf of c comma b. So let p be a partition from x0 to xn is an arbitrary partition of a comma b, and p0 be the partition obtained by including c as a point of partition in p, that is p0 equal to p union c. If c belongs to the kth subinterval xk minus 1 comma xk, we have modulus of f of xk minus f of xk minus 1 less than or equal to modulus of f of xk minus f of c plus f of modulus of f of c minus f of xk minus 1. Now we consider summation of p, which can be expressed as summation of modulus of f of xi minus f of xi minus 1, and that can be expressed again as summation I varies from 1 to n, I not equal to k, modulus of f of xi minus f of xi minus 1 plus f of xk minus f of xk minus 1. This is less than or equal to modulus of f of xi minus f of xi minus 1 plus modulus of f of xk minus f of c, which is equal to summation of p naught, and hence summation of p less than or equal to summation of p naught. So now the points of p naught on the closed interval a comma c determines a partition p1 of the closed interval a comma c, and those in c comma b determines a partition p2 of c comma b. So the corresponding sums for all these partitions are connected by the relation summation of p less than summation of p naught, that is nothing but summation of p1 plus p2, and this is less than or equal to the total variation of a comma c plus c comma b. Thus vf of a comma b less than or equal to vf of a comma c plus vf of c comma b. Hence it shows, it completes the required form. Next one, total variation on the closed interval a comma ax as a function of x. Let f be of bounded variation on a comma b, Let V be defined on the closed interval a comma b as follows. V of x is equal to Vf of a comma x if a less than x less than or equal to b and V of a equal to 0. Then V is an increasing function on the closed interval a comma b. V minus f is also an increasing function on the closed interval a comma b. First, let us show that V is an increasing function on the closed interval a comma b. For if we consider a less than x less than y less than or equal to b, we can write Vf of a comma y equal to Vf of a comma x plus Vf of x comma y. That is, this we can write it as V of y is equal to V of x plus Vf of x comma y greater than or equal to 0. That is, V of y minus V of x is greater than or equal to 0, or in other words we can say that V of x less than or equal to V of y. That implies that V is an increasing function on the closed interval a comma b, and hence condition 1 is proved in this. Next, let us show that V minus f is also an increasing function on the closed interval a comma b. Let us define d of x equal to V of x minus f of x if x belongs to the closed interval a comma b. Then we consider a less than x less than y less than b. We have d of y minus d of x equal to, that is similar to d of x we can write for d of y also. So, we can write d of y as V of y minus f of y, and similarly d of x as V of x minus f of x. So, we have V of y minus V of x minus of f of y minus f of x. This expressed as Vf of x comma y minus of f of y minus f of x. From the definition of Vf of x comma y, it follows that f of y minus f of x is strictly less than Vf of x comma y, and hence we can write d of y minus d of x is greater than or equal to 0. So, since d is an increasing function, that implies that V minus f is also an increasing function on the closed interval a comma b. Next, functions of bounded variation, which is expressed as the difference of increasing functions. So, similar to the previous one, we can prove this easily. Let f be defined on a comma b, then f is of bounded variation on a comma b if and only if f can be expressed as the difference of two increasing functions. Since by the given data f is of bounded variation on a comma b, so we can write f can be expressed as the difference of two functions, say v minus d, where v is the function already defined and d equal to v minus f. Thus, both v and d are increasing functions on the closed interval a comma b. Let f be the difference of two increasing functions on a comma b. So, since an increasing or decreasing function is of bounded variation and the sum of two functions of bounded variation is again a function of bounded variation, therefore, f is a function of bounded variation on a comma b. So, here it is v minus d, therefore, f can be expressed as a difference of two increasing functions if and only if f is of bounded variation on the closed interval a comma b. Next, corollary states that the representation of a function of bounded variation as the difference of two increasing functions is by no means unique. Next, continuous functions of bounded variation. Let f be of bounded variation on closed interval a comma b if x belongs to open interval a comma b, and let v of x equal to vf of a comma x and put v of a equal to 0. Then every point of continuity of f is also a point of continuity of v. The converse is also true since v is monotonic. So, the right and the left hand limits, say v of x plus and v of x minus exist for each point x in the open interval a comma b. So, similarly it is true for f also. So, the right hand derivative and the left hand derivative of f is denoted as f of x k plus and f of x k x minus. if we consider the points A and B in between C less than y, we have the definition of v of x comma y, that is 0 less than or equal to modulus of f of y minus f of x less than or equal to v of y minus v of x. Now let us take y greater than x from the above. We find that 0 less than or equal to modulus of f of x plus minus f of x is less than or equal to v of x plus minus v of x. Similarly, we can say for the left hand derivative, that is 0 less than or equal to modulus of f of x minus f of x minus is less than or equal to v of x minus v of x minus. So, this inequality shows that a point of continuity of v is also a point of continuity of f also. Now, to prove the converse, that is a point of continuity of f is also a point of continuity of v. Let f be continuous at the end point at the point C in the open interval a comma b, then given epsilon greater than 0 such that 0 less than x less than c, which implies that modulus of f of x minus f of c is less than some epsilon by 2. For the same epsilon, there also exists a partition P of closed interval a comma b, c comma b. Say P varies from x naught to xn and x naught equal to c xn as b, such that the variation, that is the total variation Vf of c comma b minus epsilon by 2 is less than the sum of modulus of delta fk. Adding more points to P can only increase the summation of modulus of delta fk. We can assume that 0 less than x1 minus x0 less than c. This means that modulus of delta f1 equal to modulus of f of x1 minus f of c less than epsilon by 2, and hence the inequality becomes Vf of c comma b minus epsilon by 2 is less than epsilon by 2 plus summation of modulus of delta fk plus Vf of x1 comma b. Since here x1 x2 etc. x is a partition of x comma b, and therefore V of c comma b minus V of x comma b is less than epsilon. But 0 less than or equal to V of x1 minus V of c equal to V of a comma x minus V of a comma c, that is equal to V of c comma x, that is this is equal to V of c comma b minus V of x comma b, which is less than epsilon. So, this shows that 0 less than or equal to V of x minus V of c is less than epsilon, and hence it shows that the right hand derivative V of c plus is equal to V of c. So, the similar argument which proves that V of c minus is also equal to V of c, and hence it can be proved for all the interior points of the closed interval a comma b. So, next theorem states that let f be a continuous function on the closed interval a comma b, then f is of bounded variation on a comma b if and only if f can be expressed as the difference of two increasing continuous functions. So, this we have seen in the previous theorem that d equal to v minus f is also an increasing function. Okay. Next, curves and paths. The definition is let f is from the closed interval a comma b to Rn be a vector valued function continuous on a compact interval closed interval a comma b in R. As t runs through a comma b, the functional values f of t trace out a set of points in R power n called the graph of f or the curve described by f. A curve is a compact and connected subset of Rn since it is the continuous image of a compact interval. The function f itself is called a path. It is often helpful to imagine a curve as being traced out by a moving particle. The interval closed interval a comma b is though as the time interval, and the vector f of t specifies the position of the particle at time t. In this interruption, the function f itself is called a motion. Different paths can trace out the same curve. So, here is an example for the complex valued function f of t, and the trace out the unit circle x square plus y square equal to 1, but the points are visited in opposite direction. So, the same circle is traced out 5 times by the function h of t equal to e power 10 epsilon I t. Here t lies in between 0 and 1. So, here is a rectifiable paths and arc length, and the figure 2.1 express the how the path and the rectifiable arcs we have drawn. And the definition states that if the set of numbers f of a is bounded for all partitions v of a comma b, then the path f is said to be rectifiable and its arc length denoted by f of a comma b is defined by the equation f of a comma b equal to supreme of f of b such that for every p belongs to capital P of a comma b. If the set of numbers f of b is unbounded, then f is called non-rectifiable. Next theorem, consider the path f is from the closed interval a comma b to r power n with the components f equal to f1, f2, etc. fn. Then f is rectifiable if and only if each component fk is of bounded variation on a comma b. If f is rectifiable, we have the inequalities vk of a comma b less than or equal to f of a comma b less than or equal to v1 plus etc. vn minus 1 where k varies from 1 to n, and vk of a comma b denotes the total variation of f over k on the closed interval a comma b. Already the total variation we have defined. So, similarly here we consider a partition say P from T0 to Tm of the closed interval a comma b, and we have summation of I varies from 1 to n and I not equal to k modulus of fk of Ti minus fk of Ti plus 1 less than or equal to f of p, which is less than or equal to summation of I varies from 1 to k I not equal to k and modulus of f of Ti minus f of Ti minus 1 minus 2 for each k. From 2 we have the modulus of fk of Ti minus fk of Ti minus 1 equal to f of p. So, this implies that f is rectifiable, and conversely if f is rectifiable, then we have the inequality 1. So, hence the number f of p is bounded for all the partitions of a comma b. Thus, each component fk is of bounded variation on the closed interval a comma b. Here is an example for the rectifiable arc length, which can be expressed as an integrable, and similarly the given function f of x, which is continuous but not bounded on the variation. So, the graph is a non-rectifiable curve. Additive and continuity properties of arc length. So, let f is from f1 to fn be a rectifiable path defined on closed interval a comma b, then each component fk is of bounded variation on every subinterval x comma y of a comma b. So, in this section we keep fk fixed and study the arc length f of x comma y as a function of the interval closed interval x comma y. So, first let us prove an additive property, that is, if C belongs to the open interval of a comma b, we have f of a comma b as f of a comma c plus f of c comma b. So, adjoining the point C to the partition P of a comma b, we get a partition say P1 of a comma c and P2 of a comma b, c comma b, such that f of p less than or equal to f of p1 plus f of p2. That is, this is less than or equal to f of a comma c plus c comma b, and hence f of a comma b is less than or equal to f of a comma c plus f of c comma b. Now, to obtain the reverse inequality, we consider the partitions p1 and p2 of a closed interval a comma c and a closed interval c comma b. Then P is a partition as a union of P1 and P2, for which we have f of P1 plus f of P2 is nothing but f of P, and this is nothing less than or equal to f of a comma b. Since the supreme of all the sums f of P1 plus f of P2, which is the sum of f of a comma c plus f of c comma b, and hence we get the reverse inequality. Thus, f of a comma c plus f of c comma b is less than or equal to f of a comma b. So, next theorem also based on the rectifiable path, we consider a rectifiable path s of x equal to f of a comma x, and let s of a equal to 0, then we have the function s is defined as an increasing and continuous on closed interval a comma b. Second one, if there is no subinterval of a comma b on which f is constant, then s is strictly increasing on a comma b. So, by using the additive property theorem, we can write s of y minus s of x equal to f of x comma y, and this proves that S is an increasing function on the closed interval a comma b. Further, it is given that S of a equal to 0 and here f of x comma y is equal to 0. But the inequality Vk of a comma b less than or equal to f of a comma b, which is less than or equal to v1 of a comma b plus etc. vn of a comma b. So, thus we have f of x comma y is equal to 0, that is Vk of x comma y equal to 0 for each k, and this in turn implies that f is a constant on the closed interval x comma y. So, hence the condition 2 holds in it. To prove S is continuous, we can use the inequality 1 again, and hence we have obtained 0 less than or equal to S of y minus S of x, which is nothing but f of x comma y, and which is less than or equal to Vk of x comma y. So, if we let y tends to x, we find each term Vk of x comma y minus 0, and hence S of x is equal to S of x plus. Similarly, we can show that S of x equal to S of x minus, and hence which completes the proof of the given theorem. So, thank you.